Hi, Stu Schwartz from MasterMathMentor.com. This is video AB40. The topic is Separable Differential Equations, and it covers the AB manual pages 229 and 230. All the calculus you have taken so far is really a prelude to the study of differential equations. A differential equation, DEQ for short, is a mathematical statement that relates a function with its derivative. A first-order DEQ will relate the function with its first derivative. Its form is dy dx is equal to some expression involving x and or y. The goal of a DEQ is to write y, if possible, as a function of x. Sometimes the algebra of doing so is cumbersome, and it is permitted to leave the answer in implicit form. A second-order DEQ relates a function with its second derivative, and so forth. They are much more involved to solve, but the goal is still the same, to write y as a function of x. Solving DEQs is a course in of itself, and after 4 semesters of calculus in college, students will take a course on differential equations. In the AP curriculum, you are responsible for the solution of only one type of differential equation, the ones that are separable. While not necessarily initially appearing that way, a separable differential equation can be put in the form of dy dx is equal to f of x over g of y. And when cross-multiplying, we get g of y dy is equal to f of x dx. This is called separating. All the y's are on one side, all the x's are on the other. We then integrate both sides of the differential equation, getting the integral of gy dy is equal to the integral of f of x dx. Hopefully we can integrate both sides, and when we do, we will end up getting y is equal to capital F of x plus c. Because of the c, we call this a general solution. Here are some examples of separable differential equations. dy dx is equal to xy. We can write this as dy over y is equal to x dx, and we're separated. Y is on one side, x is on the other. dy dx is equal to y squared. We can write that as dy over y squared is equal to dx. Again, separated. Y is on one side, x is on the other. Or dy dt equals sine t over cosine y. When we separate, we get cosine y dy is equal to sine of t dt. But not all differential equations are separable. Some simple ones are not. For instance, dy dx is equal to x plus y. No matter what we do, we cannot get the y's on one side and the x's on the other. That does not mean that this cannot be solved, but not through the separable techniques that we will learn in this course. It is a problem for an advanced differential equations course. dy dx is equal to y minus x over x plus 2y. In the right side, the x's and y's are mixed together and there's no way that they can be separated. Or dy dx is equal to y minus e to the negative x. Again, no way to separate them. For each differential equation, we will find the general solution, and then we will take the derivative of the solution, checking to see if we get back to the original differential equation. For number 1, dy dx equals 2x over y, we cross-multiply and we get y dy is equal to 2x dx. Integrating both sides, we get y squared over 2 equals x squared plus c. And therefore, y squared is equal to 2x squared plus c. Solving for y, we get y is equal to plus or minus the square root of 2x squared plus c. An important point, you add on the plus c at the moment you take the integral. Do not wait to tack it on at the very end, as your answer will be different. Let's check our answer. If y is equal to the positive square root of 2x squared plus c, dy dx is equal to 1 over 2 times the square root of 2x squared plus c times 4x. If y is equal to negative square root of 2x squared plus c, dy dx is equal to negative 1 over 2 times the negative square root of 2x squared plus c times 4x. In either case, the negatives cancel, and we have dy dx is equal to 4x over 2y, which is equal to 2x over y. In number 2, we have dy dx is equal to y squared. Cross multiplying, we get 1 over y squared dy is equal to dx. Integrating both sides, we get y to the negative 1 over negative 1 is equal to x plus c. And that gives negative 1 over y is equal to x plus c. Solving for y, we get y is equal to negative 1 over x plus c. Checking, we can write y is equal to negative 1 times x plus c to the negative 1 power, and therefore dy dx is equal to negative 1 times negative 1 times x plus c to the negative 2 power, and which that is equal to 1 over a quantity x plus c quantity squared. But that is the same thing as y squared. 3 reads dy dx is equal to x plus sine x over 3y squared. Cross multiplying, we get 3y squared dy is equal to x plus sine x dx. Integrating both sides, we get y cubed is equal to x squared over 2 minus cosine of x plus c. And therefore y is equal to the cube root of x squared over 2 minus cosine x plus c. To check, we take the derivative and we get dy dx is equal to 1 over 3 times the quantity x squared over 2 minus cosine of x plus c raised to the 2/3 power times the derivative of what's inside the cube root, which is x plus 2 sine x. And that is equal to x plus 2 sine x over 3 times the quantity x squared over 2 minus cosine x plus c raised to the 1/3, and that is squared. So dy dx is simply equal to x plus 2 sine of x over 3y squared. Problems 4 through 6 are a certain class of important differential equations that are in the form dy dx is equal to some expression times y. We will find that their solutions are all exponential. Number 4 reads dy dx is equal to 4y. When we separate, we can bring the 4 with the y, but it's easier to leave it on the other side and write dy over y is equal to 4 dx. Integrating both sides, we get the natural log of the absolute value of y is equal to 4x plus c. And therefore, y is equal to e to the 4x plus c. We can write this as e to the 4x times e to the c. And since e is a constant and c is a constant, e to the c is also a constant, which again we will just use as c. So our solution to our differential equation is y is equal to c e to the 4x. Despite all those steps, the check is easy. dy dx is equal to c e to the 4x times 4. And since c e to the 4x is y, dy dx is equal to 4y. Number 5 is exactly like number 4. dy dx is equal to ky, so we're using a k rather than a 4. So dy over y is equal to k dx. We integrate both sides and get the natural log of the absolute value of y is equal to kx plus c, or y is equal to e to the kx plus c, which is equal to e to the kx times e to the c, and therefore y is equal to ce to the kx. The check is just as easy. dy dx is equal to ce to the kx times k, which is ky. Number 6, dy dx equals xy, is a bit different. We still separate and get dy over y is equal to x dx, and when integrating both sides, we get the natural log of the absolute value of y is equal to x squared over 2 plus c. That can be rewritten as y is equal to e to the x squared over 2 plus c, which is e to the x squared over 2 times e to the c, and our final answer is y is equal to c e to the x squared over 2. The check is just as easy. dy dx is equal to c e to the x squared over 2 times the derivative of x squared over 2, which is x. And therefore, since c e to the x squared over 2 is y, dy dx is equal to xy. 7 through 9 are done the same way, but you have to be careful. There are some tricky steps involved, and the checks involve several steps now instead of just one. 7 reads dy dx equals 2xy times sine of x squared. To separate, we write dy over y is equal to 2x sine of x squared. And we now integrate both sides. The left side is the natural log of the absolute value of y. The right side can be done with u substitution, and we get negative cosine of x squared plus c. Therefore, y is equal to e to the negative cosine of x squared plus c. And again, since e to the c is equal to c, our final answer is y is equal to c e to the negative cosine of x squared. Checking, we write dy dx is equal to c e to the negative cosine of x squared times the sine of x squared times 2x. And since c e to the negative cosine of x squared is y, dy dx is simply 2xy sine of x squared. Number 8 reads dy dt is equal to e to the y plus 2t. This is a differential equation, but now to solve it, we need to write y as a function of t. We can write the right side as e to the y times e to the 2t, and therefore we can separate, getting dy over e to the y is equal to e to the 2t dt, and we can now integrate both sides. Both sides will require some u substitution, and therefore the integral of e to the negative y dy is equal to 1/2 the integral of 2e to the 2t dt. Integrating, we get negative e to the negative y is equal to 1/2 e to the 2t plus c. And as we need to solve for y, we will multiply both sides by a negative and get e to the negative y is equal to negative 1/2 e to the 2t plus c. Solving for y, we get y is equal to negative the natural log of the absolute value of c minus 1/2 e to the 2t. The check neatly reverses the process. We get dy dt is equal to negative 1 over c minus 1/2 e to the 2t times the derivative of that expression, which is negative e to the 2t. The negatives cancel, and realize that c minus 1/2 e to the 2t is simply e to the negative y. And therefore, when we get rid of the e to the negative y and bring it upstairs, we can write it as dy dt is equal to e to the y plus 2t. Number 9 reads, dx dt is equal to 1 plus t minus x minus tx. This is a differential equation, and we need to solve for x in terms of t. At first glance, this does not appear that it can be separated, but we can do some factoring on the right side and write this as dx dt is equal to the quantity 1 plus t minus x times the quantity 1 plus t. And that will give 1 plus t times the quantity 1 minus x. We can now separate and write dx over 1 minus x is equal to 1 plus t dt, and we can integrate both sides. But before we do, we will multiply both sides by -1, making the left side a little bit easier to integrate. So we have the integral of dx over x minus 1 is equal to the integral of -1 minus t dt. From there, we get the natural log of the absolute value of x minus 1 is equal to -t minus t squared over 2 plus c. And therefore, x minus 1 is equal to e to the -t minus t squared over 2 plus c. And we can write that now as x equals 1 plus c e to the -t minus t squared over 2. The check is kind of cool. Dx dt will equal c times e raised to the -t minus t squared over 2 times the derivative of that expression, which is -1 minus t. But c e to the -t minus t squared over 2 is simply x minus 1. So dx dt is equal to x minus 1 times the quantity -1 minus t. And when multiplying out, we get -x minus xt plus 1 plus t, which is the same terms as we had in the original problem. When we created slope fields in the last video, we were given a differential equation and asked to generate a picture of the slopes of the solution to the DEQ at all the infinite points in the plane. This was essentially the general solution to the differential equation. However, if we were told that our solution to the differential equation passed through one particular point, then there was only one possible graph that would identify that solution. We called this the particular solution. In the graph on the screen, our solution goes through the point -1, -1, and hence there is the single red curve that is the particular solution to this differential equation. In the following problems, we are given a differential equation, and we are also told that the curve passes through one particular point. From there, we would like to find first the general solution and then the particular solution to the differential equation. In number 10, we are told that x e to the -t dx dt is equal to 1 and x of 0 is equal to 1. To solve this differential equation, we will cross multiply and we can write this as x dx equals e to the t dt and integrate both sides, getting x squared over 2 is equal to e to the t plus c. We can find the general solution. However, it is probably easier at this point to find the particular solution. Using the fact that x of 0 is equal to 1, which means that when t is equal to 0, x is equal to 1, we get 1/2 is equal to 1 plus c, giving c equals -1/2. Replacing this, we get x squared over 2 is equal to e to the t minus 1/2. And therefore, x squared is equal to 2e to the t minus 1. Solving for x, we get x is equal to plus or minus the square root of 2e to the t minus 1. But since x of 0 is equal to 1, that means that x has to be positive, and therefore x is equal to just the positive square root of 2e to the t minus 1. In number 11, we have dy dx is equal to 1 plus x over xy, and y of 1 is equal to negative 4. Separating, we get y dy is equal to 1 plus x over x dx. And therefore, we can integrate both sides. The integral of the left side is y squared over 2, and the right side we can write as 1 over x plus x over x. And when we integrate, we get the natural log of the absolute value of x plus c. We will now utilize the fact that y of 1 is equal to negative 4, which means that when x is equal to 1, y is equal to negative 4. So we end up getting 8 is equal to 0 plus 1 plus c, meaning that c is equal to 7. And y squared over 2 is equal to natural log of the absolute value of x plus 7. Solving for y, we get y squared is equal to 2 natural log of x, the absolute value of x, plus 2x plus 14. Or y is equal to plus or minus the square root of 2 natural log of the absolute value of x plus 2x plus 14. But since y of 1 is equal to negative 4, that means that when we take the square root, we need the negative square root. And therefore y is equal to negative the square root of 2 natural log of the absolute value of x plus 2x plus 14. While the more recent calculators, such as the TI Inspire, have built-in capabilities of drawing slope fields, to do so on the TI-84 calculator requires the use of a program. If you have such a program or a computer app with slope field capability, you can check your answer. Shown is the slope field to dy dx is equal to 1 plus x over xy. See how the particular solution, y equals negative square root of 2 natural log of the absolute value of x plus 2x plus 14 through the point 1, negative 4 follows the slope field. Number 12 reads dy dx equals y squared plus 1 and y of 1 is equal to 0. Separation is easy. We write 1 over y squared plus 1 is equal to 1, and we can then integrate both sides, and we end up getting the inverse tangent of y is equal to x plus c. At this point, we will just solve for y, and y is equal to the tangent of x plus c. Plugging in the point 0, 1, we get 0 is equal to the tangent of 1 plus c, and therefore c is equal to negative 1. Therefore, our statement and solution is y is equal to the tangent of x minus 1. Our verification is the slope field dy dx is equal to y squared plus 1, and we show the particular solution, y is equal to the tangent of x minus 1 in blue. 13 reads x plus 2y square root of x squared plus 1 dy dx is equal to 0, and y of 0 is equal to 1. To separate, we write 2y square root of x squared plus 1 dy dx is equal to negative x, and therefore 2y is equal to negative x over the square root of x squared plus 1. We are separated so we can integrate both sides. The left side is easy, y squared. The right side is, by u substitution, negative the square root of x squared plus 1 plus c, or if you want c minus the square root of x squared plus 1. We plug in the point 0, 1, and we get 1 is equal to c minus 1, or c is equal to 2. Therefore, our solution is y squared equals 2 minus the square root of x squared plus 1, or y is equal to plus or minus the square root of 2 minus the square root of x squared plus 1. Since y of 0 is equal to 1, we choose the positive value, and therefore y is equal to positive square root of 2 minus the square root of x squared plus 1. This particular function is not one that we've ever seen before. However, the slope field is a good verification along with the particular solution that our solution is correct. The last two videos are concerned with applications of differential equations. Here is an appetizer. We let P equal the number of US COVID-19 cases. We know that COVID is spread by people, either in direct close contact or by touching objects that infected people touch. So the value of P in the future is a function of the current value of P. The more people who have the virus, the faster it will spread. So dp dt is equal to some function f of p, which is a differential equation. And if this is separable, we can then solve it, writing p is equal to some function g of t, meaning that the number of people who will get COVID is predictable if no measures are taken to slow it, like wearing masks, social distancing, and hopefully a medication. Despite what politicians say, the inevitability of this is based upon irrefutable math and science. The next video will talk about applications of differential equations.